All right. Morning, everybody. So we're going to start chapter 3 today. But before I get into that, I want to review briefly what we've done so far, kind of touch base about where we're at in the course, and then look ahead to where we're going. So I graded Project 1 last night. Those of you that submitted them, they were all generally very, very good. You all generally did good jobs on those. Couple random things. Some of you figured out how to do a nice minimal multiplexer. So you can do a multiplexer, 1-bit multiplexer with 4 gates. One of you even figured out you could do it with 4 NAND gates, which I personally had never done, but that was pretty clever. Some of you did the multiplexer with more like 20 gates. There's no penalty for that. The grading criterion is strictly, is it correct? Does it work? But if you used a very large number of gates for the multiplexer, you might find it a worthwhile exercise to take 20 minutes or so and figure out how to simplify it. I think that will help you kind of get a crisper sense as to what's essential about the multiplexer. Again, if you got it working with 25 gates, congratulations. That was a lot to coordinate. But it really can be done simply. I just wanted to make sure you all knew that. Interestingly, I found that in most of the cases where there were like gazillions of gates for the multiplexer, the demultiplexer was almost always the nice, simple 3-gate thing it just needs to be. So if you had a huge multiplexer, it might be worth your while to look back over what you did and think about how can I take the mindset that led to the simple demultiplexer and think about that with the multiplexer. Another one that was kind of interesting was that the MUX 8-way 16 can be done with 3 gates. A number of you had a quite nice solution with 7 gates, using 7 MUX 16s, but you can actually do it with just 3 if you make use of the MUX 4-way as a basis for it. So other than those things, yeah, I thought the project 1s were really, really good. If you didn't get your project 1 done, try to catch up sooner rather than later. This is not a good class to get behind in. All right. So looking at our schedule then, so we have project 2 is due tomorrow night. That's the arithmetic gates. So one question that already arose with that was I had one student who was pretty frustrated with the INC 16. And the INC 16 requires you to do something you really hadn't had to do previously, which is you need to wire some gate inputs to be constants. So specifically on page 286 of the book, it's got an example of how you do that. Essentially what you can do is you can say a particular bit is going to be true or false, and that hardwires it. So if you hardwire the bit to be true, it means current will always go through it. If you hardwire it to be false, it means it's wired to ground. And then you can even do that with like multi-bits. So you can say a whole range of bits is true or false or whatever. So what that essentially lets you do is to implement the INC 16 just using an add 16 and some constants. And at that point, the INC 16 should be pretty straightforward. But I know from emails and questions that that particular gate was a source of some consternation for a student. So thought I would clarify that issue for you all. All right, so like I mentioned, yeah, so that's going to be due tomorrow. Then today is Tuesday. Yeah, so we're doing sequential logic today. Okay, so then project 3, which is going to be memory, is going to be due on Monday. And I'm going to start lecturing today about sequential logic and how memory works and the like. So, and then starting a week from today, we're going to, before we actually build the CPU, we're going to learn how to write machine language programs. And then, so we'll take some time doing that on Tuesday and Thursday. And then 2 weeks from today, 2 weeks from today, we will start learning about how to design a CPU. And so a lot of the reason for the ordering in this way is that before we work on designing a CPU, we're going to learn the language that the CPU interprets. You know, the CPU is basically just a language interpreter as a circuit. So we're going to get familiar with the language that it's interpreting, and then we'll work on the design of the CPU. So that's kind of where we're going in the next couple of weeks. Any questions? Any questions on the arithmetic aspects of the circuits? Any questions? All right. I think what I'm going to do to start today actually is I'm going to spend a little more time on the ALU and talking about how the ALU works and how it produces different kinds of calculations. And then we'll get started on the sequential circuits. So let's review the ALU. So the ALU has the following inputs and outputs. So there are X and Y, and these are 16-bit inputs. There's then a series of 1-bit inputs that control how these inputs, these X and Y inputs, are affected. And so those included ZX and ZY, which zero them out, cause them to be all zeros. There's NX and NY, and those apply a not to them. And something we talked about last time is that if the ZX and the NX are both set, the net effect is to say, I'm getting all ones. And why is that? It first zeros everything out and then negates it, turning all the zeros to ones. Then there is the F bit, and the F bit controls whether you've got the ALU performing an AND or an ADD. Okay? So if it's a 0, you're going to get an AND. If it's a 1, you're going to get an ADD. And then NO is whether you negate the output. So at the end of class last time, what we did was we set up these values to produce a not. And so the way that we did that to produce the not, so effectively it was not of X specifically, right, was we set ZX to be 0, we set ZY to be 1, and then NX and NY were also both 1. So, and then we set F to be 0. So what was the net effect of this? We preserve X coming in, okay? Having preserved it, we don't preserve Y. We zero Y out. We then not both of them. So by knotting Y, we turn all zeros into all ones. All ones is what's known as the identity operator for AND. In other words, if you AND anything with ones, you just get the other argument. Okay? By negating X, that's how we knotted the bits in X. So we AND all of those with a bunch of ones, which leave them alone, and then NO we set to 0. And that gives us a not. Now note that this would also still work if we set N0 to 1 and NX to 0. It doesn't really matter if we knot it before we AND it with all ones or after we AND it with all ones. Either way, it'll work. And so that's how a not is implemented using this ALU. This might seem like a really extreme way to simulate a nice simple NOT gate, which as we know is easily formed by a single NAND gate. The issue here is not so much how do we make it possible to do it, so much as how do we decode a machine language instruction to tell us what we're doing. That's really the ALU's job. See, every machine language instruction is just going to be a bit string of 16 bits. And then what we're going to be doing is grab 6 of those bits and send them immediately to the ALU. So setting up the ALU this way enables the decoding of an instruction aspect to be as simple as possible. And that's why it's done in this somewhat bizarre way. Cool. Any questions so far? Yeah, Innocent.
I kind of don't know how to structure my question, but
go for it.
The way I sort of think about it, we used an ALU to create a NOT gate that way.
Yeah.
What operation happen under the hood that makes those things work? Like, for example, if a ZX was a 0 and a 0 was a NOT,
right.
You have some ends in between to sort of mix things up.
So it's a great question, and of course, it's part of what you're doing in Project 2. The answer is multiplexers. You're going to multiplexer your heart out building the ALU. You're going to have mux 16s right and left. Right? So it's not all that hard to see, right? If you think about NX, do I negate X or not? NX will just be a select bit for a multiplexer. The inputs to the multiplexer then are going to be the original X, and that same X passed through a NOT gate. So those are 2 inputs for multiplexer. That's a select bit, and then you get your output. So you're going to be having multiplexers all over the place in your ALU. Another interesting way to think about this is to observe that the ALU, in effect, is simultaneously performing all possible arithmetic operations. It actually does everything all the time. The multiplexers control which of those everythings is the actual output. But it's actually like simultaneously trying everything. And then the multiplexers let you pick among the everythings that it's trying. Cool. Other questions so far before we look at a few other operations this can do? Okay, so yeah, let's consider some other possibilities here. Oops. So we're going to do a couple easy ones, and then we're going to think about some more intricate ones. So what do I mean by an easy one? Let's say I want to do X and Y. How do I set the Z's, the N's, the F, and the NO? This is an easy one. So I want X and Y. I have to pick values for all 6 of these. Yes?
This is kind of thing, honestly, might be right. I can put, since 1 is always an identity element, I can put ZX and ZY and NX and NY, all of them into 1s, and then kind of mess with X and Y's by using an AND operation on F, and then return output.
So I'm a little confused by that. We want X and Y, so we don't really want to obliterate them, do we?
Oh, those things have effect on them?
Oh, yeah. Yeah.
Okay. I thought inputs X and Y comes independently, and you can use those.
Right, they come independently. But now we need to decide on these 6 bits, how do we produce the target operation?
Okay.
So the question is, how do we set these 6 bits so that we get X and Y? Yeah, V.
do we zero out X and Y and then negate them?
Well, why we want X and Y, so we don't want to zero them, right? We just want X and Y. Yeah, Paxton.
We just set X and Y equal to 1 and then everything else is 0.
Well, X and Y, they're just coming in. Okay. The ones I'm asking about are these 6. So X and Y are just 2 values coming in. We want to know what X and Y is. So how do we set these to get that?
Ask a question.
Yeah.
When you say Zx equal to 0, does that convert everything in X 0?
No, it means you don't convert anything to a 0.
What do you do? What happens?
Nothing.
Okay.
Yeah. So if you set Zx to 0, X just passes on in. If you set Zx to 1, X is replaced by all zeros. Yeah, Paxton.
So would you just have everything as a 0?
Yep. Right. So if you set all 6 of these flags to zeros, you get X and Y. Let's think about why that is, right? Zx and Zy are 0. That means they're left alone. Nx and Ny are 0. It means they're still left alone. F is 0. It means we perform an AND. No is 0. It means we don't negate it. So if you have all zeros, you get X and Y. So somewhat more subtle is this. How are we going to get X or Y? By setting the ALU flags. Well, let's see what that would do. If we set Zx to 1 and Zy to 1, what do we get? Yeah, and then we set Nx and Ny to 1, we get all 1s. Then we get add, so we have all 1s plus all 1s, which will be all zeros. And then we negate it. So if we set it all to 1s, we get all 1s. Yes, Andre.
You just set Zx and Nx to 1 and Zy and Y to 0.
Well, if you set Zx to 1, your X is replaced by all zeros. And by setting Nx to 1, it becomes all 1s. So if we have all 1s combined with Y, are we ever going to get X or Y?
So Zx is 0 and X is 1.
Okay, so let's say you set Zx to 0 and Nx to 1. What are you doing with the Ys? Remember, we want OR. You got an answer?
No.
Okay, just twirling the pencil thoughtfully.
Does it help to think in terms of what happens between ORing 2 bits? Like
Absolutely.
Maybe 0.
Right, because what we're doing to any 2 bits is the same thing we're doing to all 16, right? That's one of the lessons of AND 16 and OR 16. You're just doing the 1-bit operation 16 times. Right? So yeah, it absolutely helps to think that way. So let's think that way for a moment. Right? So what you've got to work with then is the following. You can have not X and not Y. Those are resources. Why? Because you can use Nx and Ny to produce them. And then you can do an AND with any 2 of X, Y, not X, not Y. And you can also negate the output if you want. So those are your resources. How do we produce an OR? Yeah, so this is our target here. This is our goal. Yeah, and because we can, yeah, Andre,
Not X and not Y and then not the opposite.
let's try that out. So if we have not X and not Y, that gets us 1, 0, 0, 0, right? And so the key insight here, right, is if I have not X and not Y, my 1, 0, 0, 0 turns out to be precisely the complement of OR, 0, 1, 1, 1. So to produce OR, what I wind up doing is setting NX, NY, and NO all to be 1. And I leave the other 3 as zeros. And now my ALU has produced OR. This is, of course, also how you essentially built the OR gate, right? So that's an interesting one. We're going to look at some others, right? So let's imagine X plus Y. What are we going to do to get X plus Y? Just set F to 1. Leave everything else alone, right? You set F to 1, you get add. And then you don't want to do anything to X and Y. All right. Let's say you just want X. You want X unadulterated left alone. Nothing done to it.
Might probably nothing.
What's that?
I'm trying to think. That means everything is probably gonna be 0 and let's see.
You're gonna wanna set ZY and Y to 1,
Mm-hmm.
and then F to 0,
And what about NO?
and O to 0.
Yep. Yeah. So if you leave ZX, NX, and NO at 0, and F at 0, and you set ZY and NY to 1, you just get X. Here's another. What about Y, if I just want Y?
ZX and NX, the one nothing changed.
Yeah, exactly. So now we're going to go from easy to extremely tricky. Negative X. So before we walk through this, I'm going to review with you all 2's complement arithmetic. So we went through this last time, but it's worth reviewing. So if I've got some binary value, I'm going to do a 4-bit value just for demonstration purposes. So let's say I've got 3, 0, 0, 1, 1. To get negative 3, I flip all the bits, and then I add 1. And I get this. And so this is negative 3. And the reason this makes for a good negative 3 is if I add positive 3, I get 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. Bam. Negative 3 plus 3 is 0. Yeah, it's a good property. It's a good property, okay? So in effect, of course, what I did was I did a not, and then I added a 1. So with this ALU, it's a little bit tricky, right? But we effectively need to not our X and add 1 to it. So how do we set the ALU flags to produce a negative X? Again, looking at the 2's complement operation, we need to negate it and we need to add 1. So how do we do that with setting these flags? Yeah, V.
So we do Zx is 0.
Okay.
Y is 1.
Okay.
X is X be 0,
Okay.
and Y would be 1.
Okay.
F would be 1.
Okay.
And NO.
And O would be 1. All right, so let's see what happens. So again, we're going to imagine it at 4 bits and just see where we wind up, and we might debug it a little bit, but there's clearly some very good ideas here. So so we're going to imagine our 3 coming in, 0, 0, 1, 1, okay? So our 0, 0, 1, 1 comes in, and it's left alone because Zx is 0. Zy is 1 and Ny is 1, so we know we've got 4 1s coming in. Nx is 0. So now we add these thanks to F being 1, and we get 0, 0, no. 0, I'm sorry, 1. And let's see. So 1 plus 1 is 0, carry a 1. 1 plus 1 plus 1 is a 1, carry a 1. Oh yeah, full adder. There we go. 1 plus 0 plus 1 is 0, carry a 1. 1 plus 0 plus 1 is 0, carry a 1. And this we then negate. So that gets us 1, 1, 0, 1, which is what we had. Neat. Good job. So now comes, kind of a some subtle and tricky things. Of course, this whole thing has gotten so messy, I'm going to have to redraft it or something. Here, I'll just scroll aside. So I'll review what our flags are. NX, NY, ZX, ZY. Oops, I have those in the wrong order. ZX, ZY, NX, NY, F, NO. Okay? So now let's think about something like this. Let's imagine X minus 1. How might we do X minus 1?
Can that be like x and a negative of 1?
Yeah.
So that would be something like keep x is 0 equal to 0, n is 0 equal to 0.
So you've got ZX is 0. What else do you have at 0?
Nx.
Okay.
Because I want to preserve x.
Absolutely. Yep.
In doing so, then I will do ny will be, okay, ny will be 1.
Mm-hmm.
Oh, if ny is 1, that, okay, if ny is 1, that makes everything 0?
No, NY1 just flips all the bits in Y.
I want to make everything 0 and convert them to 1. That would be something like zy equal to 1,
Good?
and then ny equal to 1 to flip them back
Yep.
to 1.
So you've got zeros for ZX and NX. You've got 1s for ZY and NY. So you've got X coming in as it was, Y coming in as all 1s. Now what do we do?
Okay, can I reuse maybe the thing twice? Can I use it once to negate negative 1?
No, we got to do it in one operation.
Okay.
Anybody remember what -1 is in 2's complement For any number of bits, what's negative 1 going to look like?
All ones.
It's all ones. So check it out, Innocent. You've already given us negative 1. This is negative 1.
I see.
So now what do we do? F is 1 to do add. And then what about NO?
It's 0.
Yeah.
Don't do anything.
Bam, x minus 1. And notice that we can actually do y minus 1 similarly, right? If we set zx and nx to 1s and zy and ny to 0s, we actually get y minus 1. So now, here's the really fun one. What is x minus y? Yeah.
ZX and NX is 0, and then ZY is 0, and Y is 1, and F is 1.
So you set zy to 0, and then you set ny to 1, f to 1, and what else? What about no?
1.
Okay. Let's try it out. So we'll try this just with 4 bits, just to keep things simple, right? So let's imagine we're going to do 3 minus 2 as an example and see where it takes us. So I've got my x is coming in as 0, 0, 1, 1. My y is coming in as 0, 0, 1, 0. Now we're going to mess with things. So I'm going to negate y. So now y is 1, 1, 0, 1. Now I'm going to add my x and my not y. And that's going to give me 1 plus 1 is 0, carry a 1. 1 plus 1 is plus 0 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. So I get all zeros. And now I'm going to negate this, and so I get all 1s. So this is really interesting. I got negative 1. So it turns out this actually gave us y minus x, which is just to say that there was a lot of real insight here. There was some really good insight here about how to produce our target value. It just wound up being negated. So if that gives us y minus x, what do you think we would do for x minus y? Yes?
Set NO equals 0 instead.
Well, if we do that, then 3 minus 2 equals 0.
The next one is NY 0.
There we go. So if we set zx, ny, and zy to 0, and then we set nx, f, and n0 to 1, we actually get x minus y. So this was a little bit weird because, in effect, we're having to, because we don't have a plus 1 readily, we sort of simulate it just by doing a raw invert and then flipping things around. So that one was pretty fun. In general, you don't actually have to derive any of these. There's a table on page 37 of the book that actually illustrates all these operations. But the reason I'm going it through with you now in this way was that I didn't want you all to look at that table and see those flags as just kind of magically producing these operations. I wanted you all to see that you can actually derive them, right? Just by understanding the impact of setting these flags in these various ways. So this is a really powerful operator, this ALU. If it can do and or for arbitrary binary values, ultimately, if we can take any conditional, like something we would use in an if or a while, then we can have the ALU process it. Similarly, if we can add and we can subtract, once we have some mysterious ability to do loops, which we don't yet have, then we can multiply and we can divide. With the ability to negate and inverse and not, essentially universes of possibilities are opened up by this ALU design. Cool. Any questions on the ALU? And now's a great time to ask, because between now and tomorrow night, each of you should be producing one. Yeah, Andre.
Question.
Yeah.
Like sometimes I'll get bus width errors. Is that just when like you have a result that's supposed to be like 16-bit, but you get the answer for like a 1-bit?
Bingo. Yeah. So let's talk about that. So Andre is mentioning getting bus width errors. A bus in circuit language is just a connection between two circuits. The bus width is how many bits are in that connection. So in project 1, our bus widths were either 1 bit or 16 bits. Now, in this current project, they're largely either 1 bit or 16 bits, but it can be easy to screw things up. Like when you're doing the ink 16, you have to make sure that you've got 16 bits of input on the Y bus. And then likewise, if you just sort of have a polarity problem, like you route a 1-bit X into an AND 16 or whatever, you're going to get a bus width error. Yeah. So if you see that, there's some kind of a mismatch in the pins. Good question. Yeah, V.
So on one of the kids, I don't remember which one, but I had to narrow it down to 0. I've been trying to figure out what that means. So instead of counting down from 0 to 15 for a 16-bit chip, like for the multiplexer, I may be doing 0 and then 2 1s, or 1 2, 2 1s, and 4 0s. You know what I'm talking about? Or
I'm a little lost now.
yeah,
That's-
me too. Hold on.
That's okay.
I might just email you now.
Not a problem.
Okay.
Yeah, or come by. I'll be happy to chat. Yeah. Cool. Other questions on what you need to know to build an ALU? I mean, actually, what we went over today is just how to use the ALU. But I think knowing how it's used helps inform your understanding of how it's built. For building it again, all I can say is multiplexers, and then multiplexers, and with a helping of multiplexers on the side. Yeah,
Could you expect to have maybe like 10 multiplexers in there, or maybe?
easily.
Oh, okay.
I don't think it's going to be 10. Right. Actually, you can think about it this way. The number of multiplexers is indicated by the number of select bits that are obvious. You know you have at least 6 multiplexers because each of these input flags is going to be a select bit for a multiplexer, right? Because you've got NX, right? So NX is going to need a multiplexer. ZX is going to need a multiplexer. Each of those is going to need a multiplexer. You might find you need more than that, but you certainly won't need less than that. Right. And I'd much rather use multiplexers than try to figure out how to decode all that stuff with ands and ors and nots. Right. That's sort of putatively insane, right? Yeah. Yeah. Multiplexers are your friend with the ALU. They are your most powerful ally. Definitely. Oh, one other aspect of the ALU. So the ALU, in addition to input flags, I almost forgot to mention this, has output flags. Okay? And those are ZR and NG. Okay? NG is a 1 if your output is a 1. This one is pretty easy because all you're really doing is figuring out is the leftmost bit of your output a 1. ZR,
a max to make it to get the output into the select bit and then see which came either one or two, A or B. If it was B, if it was A, then it was a 0. If it was B,
Yeah.
Just use an OR, and if it comes up to a 0, it's 0.
Right, you basically just want to OR all 16 bits. So in the last assignment, you did OR 8-way, but you have 16 bits. Now, it's not part of what they require, but I found in constructing my own solution that it was easier to build OR 16-way out of 2 OR 8-ways and then use OR 16-way in the ALU. So I have actually structured the assignment so that you get credit for creating an OR 16-way. So build that first. So let me show you what I mean. So if I go over here to project 2, I want you to build OR 16-way as a separate step. So I've provided the skeleton HDL, the CMP, and the TST files for it. And then with the test cases, you'll get your half adder and your full adder and your add 16. With these 3, you've got everything you need for the ALU. INC16 is going to be useful in the CPU proper, but not so much in the ALU. Now there's this odd test, ALU no stat. ALU no stat is test and make sure that 16-bit output is correct, but don't check the ZR or the NG. Yeah. So then, OR 16-way lets you do the ZR, and then ALU.test also tests those output flags. So this is kind of a nice order to do it because you can get the bulk of these ALU operations correct without worrying about the output flags by using this ALU no stat test. And then you can come back around, get those last 2 flags working, and then finish it off. So that's the order in which I recommend doing it. All right, cool. Any other questions pertinent to ALUs? All right, I'm going to clear this out. And we're going to start thinking about RAM. So everything we've done so far has been what we might call either a stateless or memoryless circuit. That is, you have some live electrons representing inputs, and you spit out some live electrons representing outputs. But nothing we've done so far remembers anything. And in order to really have a device that's worthy of being called a computer, requires a memory. If for no other reason than to say the very idea of a loop requires remembering what you just did and what you're about to do. See, with what we've got so far, we can conceptualize what it would mean to build a circuit that essentially does what an if statement does, right? If you've got an ALU, you do some comparisons. Maybe you've got a big network of things to do a complex comparison. And then ultimately, you compress it down to a single bit and you say, multiplexer, here's my select. So in principle, we have the resources to do something like an if. But without memory, we cannot do something like a while. Now, why would I say that? The idea of a while loop requires the notion that something changes over time, right? If you're going to build a nice, good while loop, there had better be some reason for that poor loop to terminate. And for that loop to terminate, it means that something was true that is no longer true. So there's a notion of time. Something was true at one time, became false. So that requires us to be able to build circuits with memories. So what we're going to do at the rest of the period today is slowly develop a notion of circuits with memories. And we're going to go through a couple of levels of abstraction to get there until we get to something that is useful and usable. So the stuff I'm going to go over today, I'm not only going to give the truth tables, I'm going to build out the circuits. These particular circuits you won't be creating, but I want you to see how they're still emergent from the NAND idea. The chapter 3 assignment is going to have as a starting point a circuit called a flip-flop. And what we're going to do today is get from basic logic gates up to the level of a flip-flop. And then a flip-flop will be provided and you'll work around from there. So I'm going to posit for you all what a truth table for a circuit that has memory could look like. And this is a really simple idea. And this circuit is going to be called an SR latch. So what does SR stand for? It stands for set, reset. Now, in order for this SR latch to remember things, what we're going to rely on is the idea that one of the inputs to the circuit is its own output. So in order to produce memory, we need a circuit with a loop in it. And when I say a loop, I'm not talking an abstraction like a while loop. I'm talking a loop like you use for tying your shoes. So the output has to be an input. So I'm going to build a truth table with 3 inputs, 2 of which are like normal 1-bit inputs, and the third of which is its own output. And I'm going to use kind of the traditional names for this with an SR latch. So we have SR. The output is traditionally known as Q. So we have Q in and Q out. So when S is 0 and R is 0, it doesn't matter what Q in is. Q out should just be Q in. Now what does this mean? Set is about saying, latch, I demand you to be a 1. Reset is about saying, latch, I demand that you be 0. So set is 1 and reset is 0. We don't really care about Q in. We want Q out to be a 1. Similarly, if set is 0 and reset is 1, we don't care about Q in. We want Q out to be a 0. We really, really don't want this to happen. In practice, we can build it so that in this case, it works the same as a reset. But set and reset both being 1 would be considered inputs outside the domain of the function. It's not an input the circuit's designed for. In other words, we should be unambiguously telling it, you're either setting or resetting. So let me walk through with you what this circuit can look like. So actually, I'm going to rebuild the truth table using Q in. So this is sort of a summary version. But we're going to actually spell it out now. So this is going to require an 8-row truth table. Okay. Some of the rows are going to be more important than others. Oops, I got a little big. That's okay. We'll just move around as we need to. And then this is what it was. So now we're going to go ahead and fill in Q out. So if S and R is 0, we just want to keep Q in. If S is 0 and R is 1, we want a 0. So in other words, this is our memory. This is our reset. Now, when S is 1 and R is 0, we want a 1. This is our set. And then this last block is kind of our ill-defined state. But what we'll find is it's pretty straightforward to output zeros in these situations. So having built this truth table, let me shrink it down a bit, we can now think about what kind of CPU logic, or not CPU logic, basic gate logic can we use to produce these various results. So I'm actually going to go ahead and show you what the resulting circuit is like. And then we'll use this truth table to see how it works as a practical matter. So we're not really doing this much in this class, but there are some traditional shapes for what the basic gates look like that I'll be using. So we're going to use one OR gate, one AND gate, and one NOT gate to do this. So you've got S and R coming in. And this is an OR gate right here. So S is going to be one of the inputs to that OR gate. The other input, we're going to hold on for just a moment. R is going to go through a NOT gate. And NOT gates look like a triangle with a circle on the end. And both of these are going to go into an AND gate to produce Q, and now here is our loop. We are going to OR our output back with our input. All right, so how does that relate back to this truth table? If we OR S and Q in, we then AND it with NOT R. So I'm going to go ahead and add NOT R to this truth table so that we can better visualize its role. So again, what we're doing is S or Q in and NOT R. And I'm just going to build this off in this direction. So if I have S or Q in 0 and NOT R, I get 0. So whenever S and Q in are 0, R just sort of gets obliterated. So let's look at the situations where that applies. It applies here when we want to remember a 0. It applies here kind of accidentally when we want to reset. Really what controls the reset is that the NOT R has become a 0. Then, and that's it. Those are the two situations it applies. So what about when Q in is a 1? That is, we want to remember a 1. We get 0 or a 1, that's a 1. We AND it with NOT R, which is a 1, and it's preserved. So that's our memory right there. The reset basically says, well, if reset is 1, I want a 0 to come out. So by ANDing with NOT R, bam, I've killed it. When set is 1, I want a 1 to come out. So by ORing it with our Q in, we force that to be a 1. And as long as R is 0, we AND it with a 1, and we're good. Now there's that ill-posed state where S and R are both 1. It's like we're trying to set and reset at the same time. It doesn't really make any sense, but if you build the circuit this way, inevitably you get a reset. Why is that? Because of this AND gate over here. Whenever that reset is a 1, only zeros come out there. So this is a nice simple circuit with memory. Then you might wonder, well, what happens at the beginning of time when you first fire up the electrons? Well, let's think about it. Let's say the power is turned off, right? So there are no electrons flowing. So now you flip on the power, and of course this relates pretty strongly to the idea that when you turn your computer off, all of the RAM dissipates, right? So you can see it physically here. So now you turn the power on. Electricity begins flowing in. What do you all think Q in is going to be at this point? You know, the electrons are marching in now that we've turned the power on. They hit this wire, they hit this wire. They keep marching through. What's Q in going to be when the electrons hit this OR gate? It's going to be 0, right? There weren't any electrons there to begin with. So, like, beginning of time, yeah, Q in is going to be 0. That said, at the beginning of time, what we really want to do is hardwire the circuits that are starting up our computer to do resets on everything, or sets, so you've got a nice, well-defined value. You know, you certainly don't want to rely on a particular Q in at startup. You want electrons hitting one of these at startup. Yeah.
Since the input value is defined to be the output of the circuit itself,
Yeah.
like how do you know the beginning charge value? Since you know we're only seeing S coming,
Right.
but
Yeah.
or has to have 2 inputs coming in.
Yeah. Essentially, it's like I just said. When you power on the computer, there's no charge there.
Okay. Oh, so it's 0. at
Yeah.
the beginning.
Yeah. You know, because this can only remember anything as long as electricity is flowing through it. Right? This isn't physically capable of remembering without electricity flowing. So inevitably, of course, it lets us wonder about flash RAM. Flash RAM is not built this way. Flash RAM actually requires physically trapping electrons in layers of silicon, which is extremely cool, but not built out of NAND gates. In this way. NAND gates are actually involved, but yeah, flash RAM actually involves trapping electrons within it. It then has this interesting property that every time you erase flash, you inevitably dislodge a few atoms of silicon, which means if you erase it a whole bunch of times, it eventually wears out and loses its ability to remember. Yeah. So yeah, USB drives actually don't last forever. You don't want them to be like your ultimate backup. It's an interesting problem. Trust me, the flash RAM manufacturing people think really hard about this stuff. But yeah, but this very simple loop allows us to have memory in a circuit. Now, so is everybody with me so far as to how this works? There's no magic here, right? There is a bit of cleverness, but there's no magic here, okay? This actually gives us memory, and once we have memory, now we can do all the computer things we're used to. Loops, variables, all of that stuff. But an SR latch is not terribly easy to use, right? It's not something that we directly want to build a memory out of. We want to use it as a component, though. And that we're going to use it as a component for what is called a D latch. D stands for data. So SR is set, reset. D is data. So what's the idea of a data latch? the idea of a data latch is that you've got two main inputs. D for data and S for set. Okay. And the truth table for these is going to look something like the following. And then you've got your output, which is still traditionally Q. So let's just set up the usual truth table. Let's say your data line is, actually I should have done that. Well, we're gonna start with set being 0. Set being 0 means you just want to go with whatever you remembered. So you're going to ignore data and you're just going to spit back out your Q in. Set being a 1 means you want to change what you remember to be your data input. So what we can actually do is rebuild this truth table in terms of what are the inputs to an SR latch. So what would that look like? Well, if data is 0 and set is 0, S and R are both going to be 0 because you don't want to change what you had. Similarly, when data is 1 and set is 0, S and R are still both going to be 0. In other words, if set is 0, we don't really care what data is. We just want to preserve what we had. What if data is 0 and set is a 1? Somebody told me. So set is 1, so we're going to change. Data is 0. What should S and R be? Yes?
Would S be 1 and R be 0?
Yep. And why would S be 1 or,
Oh, I got that.
yeah. And I interpret, yeah. You probably meant it this way. Why would R be 1 and S be 0?
That's because you want to reset the data value. So
Yeah.
R.
Yep. What if they're both 1s? Then what do we do?
S1 R0?
Yep. S is 1 and R is 0. So this idea of a D latch is a really nice abstraction on top of the SR latch. The reason for that is imagine stuff like your OR gates and your half adders and so forth. Those all output data bits, 1s and 0s. What the D latch does is it says, okay, the output of your mathematical circuits can directly be an input to this latch. And we then have some means of deciding whether we're letting the input in. It's like the data is this rushing stream of water, and the set bit is whether you lift the floodgate or keep it closed. So as a circuit then, this is fairly straightforward to create. Just looking at it right, R is just not data and set, right? You're not the data and it with set. That gives you your R value. Because if it's not data and set, that's when R is 1. Otherwise, R must be 0. And then S is just data and set. When those are both 1s, then you get an S of 1. So this is very simple logic that we prepend onto that. So the D latch is pretty cool. Now we've got a memory that can receive a bit of data. And then we just decide if it's coming in or not. But now here is the really tricky part, is deciding whether or not it's coming in. So you build a circuit, the electrons hit different parts of the circuit at different times, right? So what we really need to do is make sure that all memory updates happen at exactly the same time. By making sure all memory updates happen at the same time, we make sure that whatever computation we're doing is well defined. So everything's got to happen at the same time. And this is why every CPU has a clock. And this is why clock speed is such a crucial idea. The clock speed of your CPU is the frequency with which it allows memory to change. It's the frequency with which set bits on D latches are becoming ones. So this is a really fascinating way to think about the clock speed, right? The more frequently the set bits can become ones, the more frequently memory can store the results of calculations. Now here's something really important. No CPU can ever process instructions faster than the clock cycle for the RAM updates. And the reason is, an important piece of memory in the CPU is, what instruction am I processing next? And that requires memory, right? So the clock cycle then fundamentally is just how frequently do we refresh RAM? Now, of course, at this point, I want you to drop your jaws in awe and wonder at the thought that we can build circuits that refresh RAM 4 billion times a second. 4 billion times per second. That's what a 4 gigahertz CPU means. Yeah, I just want you to soak in the awesomeness for a second. All right. So what we need to do is think carefully about what it means to build circuits that are synchronized. And this turns out to actually be remarkably tricky. So you've got a clock. It's wired to every D latch. But you still have to worry about the length of the wires. And is it actually getting to all of them at the same time? So hint, it's not, right? No matter how well you engineer it, you're not going to make sure that every single memory circuit in the entire computer has the exact same wire length back to the clock. It's just not going to happen. So what we have to do is we engineer around it. And the way we engineer around it is we actually use 2 D latches to store every bit. Let me show you how this is going to work. You've got data coming in, and you also have a clock pulse coming in, okay? And you're going to have 2 D latches inside this thing. So I'm going to call this D1, and here's its S, and here's its Q. And this one is talking to another D latch, like so. Now your clock, D is just going to feed right into here. The really tricky part is the clock. So, very important idea is that the clock is always sending complementary values to the set bits on these latches. What that means is that at any given time, only one of these latches is going to permit an update, no matter when the value arrives. So the clock is constantly pulsing, right? So it goes from 0 to 1 to 0 to 1, from 0 to 1, and so forth. These clocks are basically pulsating crystal, quartz crystals, okay? And I mean, they do require power, right? So electricity flows through them, physics happens, and they emit a signal in a regular periodic interval. Yeah, that was serious hand waving. Physics happens. You'll have to tell my friends downstairs that I said that. What does this mean? So let's say I've got data coming in to this flip-flop. When the clock is a 0, this set input becomes a 1, and the first flip-flop gets updated, or the first latch gets updated. But that update is stuck here. Since my clock is a 0, that's a 1, but the clock being a 0 means this isn't allowed to be set. So this poor latch is banging on the door of this other latch saying, "Let in the data." And it won't let the data in because it's so mean. But then what happens is that the clock goes to 1. When the clock goes to 1, this set goes to 0. So this latch has its mind made up. It's going to ignore anything else coming in. So especially once stuff starts coming out of here, it's going to start propagating and trying to do other calculations, which are then going to be knocking here. And this locks those out, which is good. But now that this is a 1, this set is a 1, and it finally lets that previous data update in. And then inevitably, the clock goes back to a 0. And now this is what this latch will let in the result from the last cycle of calculations, and this one won't let them in. So basically, every time the clock pulses is an opportunity for all calculations to synchronize. It follows from this that there's a very important circuit design issue, which is the total time for an electron to travel through the entire circuit needs to be less than the pulse time for your clock. Right? Otherwise, everything goes to hell. So when you think about overclocking a CPU, which certain game aficionados are fond of, well, what does that really involve? Well, what happens is that engineers, being the careful people that they are, will actually set the clock pulse time to be well in excess of the time to propagate an electron through the circuit. They're going to allow a lot of clearance. Overclocking is saying, well, that's kind of, you guys are just so conservative, you know, it's just, yeah, that's what overclocking means. If overclocking meant just go beyond that, then that would mean hose your computer, you know.
So there's a time where like I'm using my PC and all of a sudden it kind of like bring a blue screen or something.
Oh,
That's one of those errors. Does that how they
No.
like
no, those errors don't happen in a well-engineered computer.
Okay.
Yeah, it just doesn't happen. I mean, Intel and AMD and the like are really good at their jobs. Yeah, it doesn't happen. Now, a blue screen usually happens because of some kind of software level memory corruption error. It's the kind of stuff we go into in more detail in the operating systems class, which I'll be teaching next year. Not so much in this class, but essentially what happens is the operating system winds up in an impossible state. And so then it basically sends a panic signal to the CPU, which then automatically triggers a routine in the operating system where it throws up its hands and says, Control Alt Delete me. Yeah. Yeah, which became known in the 90s as the blue screen of death. But yeah, that's the kind of thing that happens there. So that's kind of the foundation of memory in a CPU. I'm going to walk through some of this again at the start of class on Thursday because there were a lot of big ideas here. And then at that point, we're going to start thinking about how memory is laid out in a CPU and how that ties into the circuits we'll be building in Project 3. All right, see you then.